Hi again, guys. Welcome to Lecture 7 of GG497 Geological Visualization. This week we're going to look at folds and folding and how folds present themselves on geological maps. This lecture will contain a fair bit of jargon and a bit of technical term, so we might as well dive straight in to that so we can understand what we're talking about when we mean folds. So folds then, they're made out of limbs which might have different dip directions, and the point of inflection where the dip of the limb changes, we call that point of inflection the fold hinge. Now along that fold in 3 dimensions there'll be a plane of symmetry which connects all of the fold hinges at each step of the fold, and we call that the fold axial plane. And when we look at that plane of symmetry, that fold axial plane in cross section, when we look at it in perpendicular to the strike of the axial plane, then we see the fold axis. So we have a fold axis, which is what we see in cross section. We see a fold hinge, which is something that we might see in map view, and then the axial plane connects the fold axis and the fold hinge in 3 dimensions. If the limbs point upwards like they do in this picture, then the structure that we're dealing with is an antiform. An antiform, and you can think of it as making an A shape, like a capital A. It kind of peaks like this. Whereas if we had the situation where the limbs were dipping towards each other, then we'd have something called a synform, or a down-arching fold. Right, there are broadly two types of folds. One type of fold is called a cylindrical fold, and that's where the fold axis is straight, and a non-cylindrical fold where that fold hinge itself is curved. It isn't a straight line, it's a curve. So cylindrical and non-cylindrical folds, and we'll see examples of these 2 different types. Cylindrical folds then, they can either be horizontal, and that's where the fold hinge crops out at a continuous height. So if you were sat on a bed and you found the hinge, you could walk in a horizontal direction along that hinge line, so your elevation would never change as you walked along the hinge. However, some folds, they themselves can be tilted so that the hinge plunges. It's got a downhill direction to it, it's got a slope to it. So for example, if you were to be walking along the landscape and you'd be on this bedding plane, you'd be sat on the hinge, and if you were to walk along the hinge, you'd go downhill. We call that a plunging fold because it plunges down into the subsurface. Now we saw last week that folded rocks, they can be recognized by irregular or wavy contacts. They kind of look folded, and they can be also recognized by a stratigraphic repetition, like a sort of mirror image. And this is a large fold in Connemara in the north west of Ireland, and you can see that we've got these irregular contacts which come down. If we follow this blue one, for example, it goes through the countryside and then bends around to come back, so it's got that kind of irregular nature. It's not a linear feature. And we can see that there's this very obvious mirroring, like in the core of our fold here we're into our yellow, then we go into our sort of brown, and then into our blue, and we do the same thing on the other side. But it isn't always that simple. Like for example here we've kind of got something that looks like it has a mirror image repetition. We go from pink to blue back into pink, and it's got an irregular contact. Okay, so is this contact truly folded? Well, like I said, it appears to have that stratigraphic mirroring and the contact is irregular. However, just because it has those two things, you can tell that this contact is actually horizontal. It's not folded. And you can tell that it's horizontal because it's following the ground contours. So just because we have that stratigraphic mirroring and the sort of wavy, irregular, whatever word you want to use, outcrop patterns, doesn't always necessarily mean that that rock is folded. You can get something that looks a bit like that just from horizontally bedded rocks. How about this contact? Well, we can tell that this contact, it's not horizontal because it doesn't follow the ground contours. But it does seem to have that stratigraphic mirroring and that irregular nature. You've got that mirror, you kind of got a line of symmetry here, right, where you go from blue into pink back into blue, and it's kind of got this irregular shape. However, if you were to draw structural contours for this thing, you could see that they're linear. They're uniformly dipping. There isn't a fold, there isn't a kink, there isn't a hinge that we can see. It's just a uniformly dipping bed, and the reason that we're getting this wavy shape of the outcrop and this mirror image repetition is simply because we've got this V-shaped pattern that's produced by a dipping bed intersecting a valley. If you remember from, I think, lecture 3 or 4, we talked about the V rule and how contacts can V up or downstream depending on the direction of dip relative to the topography. That's what you're seeing here. So just by using those features, the stratigraphic mirroring and the wavy irregular nature of the contacts, it isn't the only thing that will help you figure out if that rock if those rocks are folded, and in fact it shouldn't be used in isolation. So how then do you recognize folded rocks? Well, the first answer might be opposing dips, and they're a pretty good indicator. If you have one of those folds that we saw in the first slide, you can see if you had an antiform, those folds would be dipping in different directions. But sometimes, if your rocks have been completely compressed, if they've been severely deformed and texturized, what you can start to do is turn your upright folds on their side. You can make them become recumbent, and in that situation hopefully you can see that if you were to measure a dip and strike of a bedding contact here, it will be dipping over to the left of your screen. But even if you went over the hinge, you can see that the rock contacts, they'd be overturned, but they would still be dipping towards the left. So not always can we rely on a fold having opposing dips either side of the hinge line. So instead we have to take a whole range of approaches. We need to understand the dips, we need to understand the topography, and we need to be aware of these mirror image repetitions of layers across the hinge zone. So for example, you can imagine that in both of these examples, if we were to take a map view, cut through this fold, we would see a repetition, a mirror image of the rock types either side of the fold hinge. So on a relatively flat land surface, you would expect the outcrop patterns of these horizontal folds, or those which don't plunge, to have some degree of mirror symmetry on it. So for example, this is a real USGS map with a horizontal cylindrical fold. So it's a symmetrical synform. You can see the dips on either side of that mirror plane. They're dipping towards each other at 40 degrees, dipping towards the northwest, and 30 degrees dipping towards the southeast. And you can see that we have this perfect mirroring of the stratigraphy either side. So that's the case where we have a horizontal fold, one where the hinge is perfectly flat, its elevation doesn't change. However, if you have a fold that itself is plunging, that is one where its hinge has a degree of dip to it, then those sorts of folds, when you see them on map, their outcrop patterns will either converge, they'll close around each other, or they'll diverge, they'll open up to be wider and wider. So for instance, if you have a plunging antiform and you were stood on this bed of limestone, you can see that if you were to follow that bed of limestone, you'd quickly go around the hinge zone and start coming down the other way. The outcrop pattern would close in the direction of plunge. If you were to be stood on a limestone bed in this synform, if you were to walk in the direction of plunge, you could see that the outcrop patterns will get wider and wider. They get further and further apart from each other. So looking at an example from our cheddar sheet, we can see that we've got these folded rocks that have these opposing dips. So on the north in our Carboniferous limestones, the dips are ranging from 60 to 55 to 50. And then on the other side, in the southern part of the fold, our rocks are dipping at 25 or 23 in the opposite direction. So it looks asymmetrical, this limb being much steeper than this. And you can see that as we follow some of the Carboniferous rocks around that fold structure, you can see that they close and bend round and come back the other way. So what we can say about this fold is that it's asymmetric. One of the limbs is much steeper than the other. It's an antiform because one limb is dipping away from the other, so it must be up-arching. And because it's an antiform with exposures that close to the southeast, then that fold hinge must be tilted, it must be plunging towards the southeast. So the example that's probably most akin to is this one from the previous slide, where we're on one of our Carboniferous limestones here. We're on one limb of the antiform, and as we go around the hinge zone, the plunge of that fold means that our outcrops seem to bend around and come back the other way. Okay, so these plunging cylindrical folds, they give themselves away by having this sort of exposure pattern. So to try and demonstrate what that would look like in 3 dimensions, if you could undo that erosion. Your plunging folds, this is what they'd look like. They'll have been folded, but they're also tilted, so that their hinges are plunging. And then if you were to imagine if that plunging fold hit a map surface, hit a ground surface, then you'd see that kind of S-shape outcrop pattern on the map. So whenever you see this sort of outcrop pattern in the map, if you can rule out it being a product of horizontal strata intersecting the landscape, or tilted strata intersecting valleys and so on, if you see this outcrop pattern, then you know that you're dealing with plunging folds. So for example, from a particularly folded area, I think this is in near Rada somewhere, you can see that these folds, they're certainly not caused by horizontal rocks because they cut across the topography. They're not caused by intersection with a valley. I mean, you know, look here, there is no valley that this is intersecting with. So this sort of outcrop pattern that we're seeing can only be achieved by plunging folds. Okay, so that's cylindrical folds, ones which have this linear hinge line, whether it's upright or dipping. It has a linear geometry. So non-cylindrical folds then are ones which plunge in more than one direction. So they can be plunging one part of the fold in one direction, then as we go to the other side of the fold they'll be plunging in a different direction. So take a minute to look at this fantastic three-dimensional exposure of a fold and see if you can figure out what the limbs are doing and what the plunge of that hinge is in different parts. Well, to me it looks like I can see the limbs of the fold, particularly where they're catching the light. You can even see the shadow on some of the bedding planes. It looks like we're dealing with an antiform because we have these two limbs which are dipping away from each other. I can eyeball a hinge line where that point of inflection of one limb changes into the other. So I can label it as an antiform. I can see in the area of the photograph closest to us, I can see as one of these marker beds that I can follow all the way around. I can see as it approaches the hinge zone, it closes and then comes back in on itself. And I'm pretty certain if I follow this bed, this resistant bed of whatever it is across the landscape, I can even see there's a hint of it starting to come around this fold, and it looks like it closes this way until it joins back up. So it looks like I've got one of these folds that's dipping in, that's plunging in two directions. Okay, so it's a non-cylindrical fold, because obviously this plunge, as we go up, it goes up, and then it starts to go down, 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 down. So it's not a linear feature, so it's non-cylindrical. And we can get a number of different types of non-cylindrical fold depending on the directions of plunge. If we were to have an antiform that kind of plunges in every direction, we'd call it a dome. If we had a synform that plunges in every direction, we tend to form a basin. But then if we have, in this example, if we have an elongate fold that plunges in opposing directions, if they're away from each other, then we'd form something called a whaleback. If it was an antiform. If it was a synform that was plunging away from each other, we'd form a shoehorn. If it was a synform where the two ends of the fold were plunging together, we'd form a canoe. And if it's an antiform that are plunging together on either side of the fold, we'd form a saddle. So looking at our example in the previous slide, we've got an antiform where the two ends of the antiform are plunging away from each other. So we've got a whaleback fold. Okay, this might be familiar sounding. I think you might have seen some of these in the field before. Can you think of potentially a folded sequence of rocks that we've had non-cylindrical folds in, even if you didn't realize it at the time? Well, hopefully you guys remember that you went to West Angle Bay in Pembrokeshire, where we saw fantastic examples of non-cylindrical folds. You remember that even in the synform part of the fold, it looked like there was a big puddle in the middle, and that's because that fold was plunging either end of it into the center of the fold. So we were dealing with a canoe-shaped synform. Okay. So on map view, you can kind of see this is a still from the Haverfordwest sheet, and you can see that we're dealing with a synform because our two limbs of our fold, they're dipping into each other rather. We've got a fold axis plotted on our map, and you can see that either end of the fold our outcrops are closing. We've got a closure here in this green unit, and if we would follow it along, it closes here again. And this is very characteristic of non-cylindrical folds. So here, another example of a canoe-shaped fold. How about this photograph then? What would you say about the plunge on this particular fold? Well, it isn't directly overhead, but hopefully you can see that it does look like it closes in every direction. I mean, it's circular, right? It hasn't got any elongate geometry to it. It looks like a circular feature that's plunging in all directions. And the only geometry that you can get this sort of exposure in is if your rocks are domes or basins. I'm not entirely sure what the dip of these beds is, but I think maybe here I can see a bedding plane, which would indicate that this is a dome, that these beds are coming up and then coming back down. So it looks like what we've got here is an eroded dome. Okay, so that's a demonstration of folds and how they appear on maps. And now what we might want to do is figure out how we might draw a cross section for folds. And there's two examples that I'm going to go through, because folds, aside from being cylindrical or non-cylindrical, they can have different shapes in cross section, and you have to decide based on the information you've got on your map what is the best shape for the fold that you're dealing with. So let's say that you went back to the Bristol sheet and you wanted to draw a cross section between points A and B in order to show this fold in cross section. Well, the first thing that you need to do is figure out, do we have chevron folding, where basically your limb has a singular dip all the way along the limb, and its point of inflection is very, very, very tight. So you just have one dip that describes one limb, and then one dip which describes the other limb, with very, very little change. You get these kind of pointy folds. Like here's a really nice example. You got one dip, one dip, one dip, one dip, change, and another dip. So you get these pointy chevron shaped folds. Or you can have concentric folds, where the dip gradually changes as you approach the hinge zone. Okay, it's very easy to see exactly where the hinge line is, or where the fold axes are for these chevron folds, but it's somewhat more difficult to find it in these concentric folds because that hinge zone, that inflection, is so broad. So ask yourselves, how do you think you could tell these two types of fold apart on a map? Well, chevron folds have uniform dips on the limbs and a very small hinge zone, so a very small area where you'd go from one dip and you'd transform into the other dip. But concentric folds have limbs whose dips vary systematically towards the hinge. So you can imagine here it would be a really steep dip, then it would be less steep again, less steep again, and then really, really, really not very steep at all. And we'd get that systematic gradual change as we approach the hinge line. So here in chevron folds we'd have one dip and then another with no kind of gradual transition. Whereas on a concentric fold you'd have a gradual transition all the way. So looking at our fold for our Bristol sheet, on either one of the limbs, all I've got on the north limb is a dip of 60, 60, 55. So the north limb has a uniform dip, it seems, of about 60 degrees. And the southern limb, it has a pretty uniform dip of around 25 degrees. There isn't in between this 60 pointing to the north and 25 pointing to the south. There isn't a gradual change. This doesn't turn into 50, 40, 30, 0 and then count up the other way. So for my money, this looks more like a Chevron fold. We've got one uniform dip describing one limb of the fold and one uniform dip describing the other limb of the fold. And I might be wrong about this, and maybe there just isn't that much exposure here to show that gradual concentric folding. But based on the map, you can be argued to be wrong in interpreting this to be a chevron. Okay, so aside from its shape, we need to know whether or not this is an up-arching thing or a down-arching thing. And I can see from the map that the structure is asymmetric and it's an antiform, and it's plunging towards the southeast. So that's the shape. That's where I'm going to end up drawing. That's the picture I've got in my mind's eye. I'm going to have a chevron fold that's asymmetric, with the north limb much steeper than the south limb. Okay, because our rocks are steeply dipping, we don't really need a hill profile or any vertical exaggeration, because we only use those if our rocks are flat lying and they'll just bunch up on a cross section. So what I can do is use my strip of paper, not have to draw my hill profile, and mark on all of my geological contacts. Oops. So everywhere as I walk along this strip that I find a change in rock type, I mark that on. And then I colour in or label the rock types that I've crossed. So my Devonian sandstones, my Carboniferous limestones, mark all of those on. And then what I want to do is annotate the strip of paper with my dip information. So like I said, just by looking at the map, I can see that these contacts over here, they have this uniform dip of about 65, and these contacts on this side of the hinge have a uniform dip of about 25 or thereabouts. So now what I can do is start plotting my geological section. And because these rocks are pretty steep, I can just draw what we call a sketch cross section, which doesn't have a topography on it. It's not that important for seeing the structure. So I take my marks and I drop those geological contacts onto the cross section line, so where those contacts would crop out on the surface. Then I'd add in the bit of colour to shade the top layer, the top veneer of the cross-section panel, just to show those rocks will be there at the surface. And because I've got no awkward faults or cross-cutting relationships to worry about, the only thing I've got in my particular cross-section is those Devonian and Carboniferous rocks that have been folded, I can just plot their extension down into the subsurface. Then what I can do is colour in and shade my cross-section to show what the subsurface geology would look like. And what I've done is estimated the thickness of those Devonian rocks, and I've tried to show that beneath them there might be some older rocks which don't crop out in the area. But I just want to let people know that there's a level of uncertainty because I can't see anything further than Devonian. I don't really know how far it goes down, and I don't know at what point we go into something else. Then I can sensibly project my stratigraphy above the ground to show where it would be prior to modern day erosion. And if I do this correctly and join my contacts and interpret where they go otherwise, I should be able to then join up my fold hinges to describe the fold axes. So we can see that this fold isn't completely upright. It's got some level of tilt to it. And then I can finish off by showing my scale and my key so that you can understand what's going on in the subsurface. Okay, so that's what our finished cross section through our fold should look like. And if we were to compare our cross section, the one that we've just drawn, with this one, you can just about see the line on the map here. This is the cross section that the Geological Survey have drawn. You can see that we're pretty similar. Yep, we've got this steep dip and less steep dip, and then we've got this fold axis, which would come somewhere down in here, something like this. And it looks like they found a little sort of minor fold on the limb of the larger structure, which we haven't included. It didn't crop out on our section line. Okay, so that's how we would draw a chevron fold, and that's the easiest sort of fold to draw because you've got one dip and then another dip and this pointy hinge. Okay, but what about if you were to have concentric folds? How would you start drawing those, where you have this broad hinge inflection of one limb going into the other? How could we draw that? Well, we have a nice example of a curved surface, like one of these concentric folds, and the method that we're going to have a look at now you can use for any curved surface where you have suitable structural information. Okay, if we look at this line of cross section, we can see that the dip, it has a change to it. So for example, in the east the dips are about 20 degrees. Then in sort of the central part, just to the east of the center line, the dips are really steep. They're about 70 to 80 degrees. Then as we go just west of central, we get a dip of 30 degrees. And then the outcrop patterns in the far west suggest that the rocks are perfectly flat. So we go from 20 degrees to 70 degrees to 30 degrees to 0 degrees all along our cross section, and they're this sequence of rocks. Okay, well, we need to show this variation. We can't just, you know, average it out, like an average of 20 degrees and 70 degrees. You know, what is the point of that? That give you an average of 45, which is completely wrong for both counts. So we need to actually show this systematic variation in dips. Okay, so what we do is, like we've done before, I'll skip a few of the steps. We'd mark on the contacts, and we'd mark on the structural information. So I've tried to simplify this a bit. I've merged some of these. I think these are carboniferous, maybe limestones. I've merged those together. I've merged some of the Devonian rocks together, and I've put some of the millstone grit and the coal measures together. But you get the idea that I've marked on the key stratigraphic boundaries on my map. Then what I do, just in the same way as we've done before, I drop the contacts onto the section to show where they'd hit our hill profile, and then I've coloured in that top veneer of the hill profile to show the rocks where they'd be at surface. Okay, then at this point what I'm going to do is make a small dash to show each contact and the dip that I think that contact is at based on its position in the map. So for example, here where I've got this dip of 20, I'm going to assume that that 20 applies to this contact between these rocks, these Devonian rocks. Then here at 70, that's very close to my cross-section line, so I'm going to assume that the rocks in that vicinity, they're dipping at 70 degrees. And then here you can just see the 3 and the 0 peeking out here. I'm going to assume that that 30 degree dip applies to these, so I've made a small dash at 30 degrees there. And out here, these rocks, which are the contacts which are parallel to the ground contours, I'm going to assume they're horizontal, so I've marked those on as small dashes of horizontal. Okay, so I've got these small dashes, and at some point I'm probably going to rub these out and modify them. But we now have a problem that if we didn't think about this and just projected the top and the bottom of these contacts, let's use the pink layer for example, it would pinch out entirely. So if we just continued this and continued this, it would just pinch out and we just have this weird wedge of Devonian rocks. Okay, and that's not likely. It's not even like, I think probably not even geologically possible. So what we need to do is figure out a way to get past this, while also acknowledging that sedimentary rocks tend to have fairly uniform thicknesses along strike. So you can see this nice marker bed. We're going to follow it around this big beefy guy that's cropping out on this mountain as well. You follow it around, it has a pretty uniform thickness all the way around. Okay, so forcing one of our Devonian rocks to change from, I don't know, however many hundreds of meters of thickness this is here to be 0 meters of thickness there, it's just not geologically feasible. Okay, so how do we draw it then? Okay, well the way that I would do it, and this is something called the kink band method, and you can Google this and find other descriptions elsewhere. What you can do is draw a line and focus in on this pink Devonian bit of rock. You can draw a line which is perpendicular to the top contact and extend that line into the subsurface and mark on where it would intersect the projected line of the bottom contact. So I've got this bottom contact that's dipping at 30 degrees, so I extend it down into the subsurface in this direction. And I've got this top contact which is dipping at 70 degrees. So I've taken a line which is perpendicular to that and I've marked on the intersection. Okay? Now in order for this rock to maintain constant stratigraphic thickness, at the point that I've marked, at this star, the dip of the bed must be parallel to this top contact. Okay, so at this intersection between the two lines I've drawn, at that point there, the dip of this contact must be the same as the top contact in order to keep this rock the same. Now that thickness there, I can use that as a proxy for my true thickness measurement for the pink unit. So I can measure this length, and this bed, this pink bed, must be that thickness everywhere. So what I can do is go to my bottom contact, I can measure that thickness, that same thickness that I've just derived here. I can measure a line perpendicular from the contact, that same length, and in order for this rock to maintain stratigraphic thickness, I'd have to dot in my contact thusly. So you can see that the thickness here between the top and the bottom of the bed is the same as this thickness here. So in order to maintain constant stratigraphic thickness for this unit, I have to bend, I have to kink these beds around in this fashion. Okay, so you can watch that several more times. But what we could do is continue with our cross section. We can repeat the process for each of the other contacts, remembering to keep the true stratigraphic thickness constant. So for example, I'm going to draw a perpendicular line from this contact here, and at each one of these intersections the beds must kink to be parallel to that top contact. And then if I were to continue these lines down, where we meet these contacts in our carboniferous rocks, everything beneath it is also going to have to be horizontal as well. Okay, so we've marked on the intersection of this continuation of this boundary and where it intersects with this boundary. So at that point we must have a point of inflection in order to maintain constant stratigraphic thickness. So this process can be fairly involved, so I bring a rubber and I do this in pencil for sure. But hopefully you can see that by repeating this process you can get a realistic representation of the stratigraphy. You can show that constant thickness, and you're being true to the structural information. You're not averaging anything, you're not changing anything, you're not getting rid of an awkward dip. You're taking all of it into account and giving a geometric representation which fits, which is defensible, which agrees with the map. Okay, so by adding color we can make a section which is both consistent with the dip data and has a consistent true stratigraphic thickness. Okay, we call this the kink method, and there's a website at the bottom of the screen which has a really good blog and step-by-step and some complex examples for you to work through. But hopefully you can see that if we were to compare our rough PowerPoint method with the actual cross-section for this part of Newport, you can see we're pretty close, right? We start off with a pretty low angle dip that then steepens up, and that's mirrored as we go through the stratigraphy until we get further to the west where our carboniferous rocks, they're on that steep dip and then they flatten out. Okay, so just like what we've got steeply dipping carboniferous rocks which then flatten out. But the only difference between ours and their cross-section is that ours, I guess, is a little bit, for want of a better word, it's a little bit kinky. And kink banding, it is a real phenomenon that you see in geology where you get this uniform dip, kink, change in dip, kink, change in dip. But perhaps a more common or realistic geometry is this concentric folding. So what we could do is turn our kink banded section into a concentric folding section. It requires a bit more interpretation and a bit more graphic or drawing or geometric skill. But you can see how you can turn your section into something that looks more realistic. Okay, so now our lab is looking at this Newport sheet fully. So that example that we've just done with the concentric folding, that was taken from the Newport sheet. So now what we're going to do in our lab is go forward with Newport and have a look to see if we can draw ourselves some folds, some concentric folds in cross section. Okay, well, thanks guys for listening. I'll see you for our next lab. Take care of yourselves, and I'll see you in a little bit.